All right. Let's do this. No, so we're waiting for your votes. Yes. Okay, yes,
Usually you can report the review section. So you get.
I hope so. I mean, I mean, unless the thing was, I'm planning to record it. Yes, for, a best experience, I recommend being here, but yeah. Any questions about the logistics of the exam? So. Don't forget that we have a review session 6 o'clock right here this evening. Yes, did you have a question?
Yeah, is the exam curve too, or is it just the quizzes?
Okay, so, no and yes, in the following sense. So here's what I did. I'll be transparent about my grade. So you guys already know the deal about the quizzes, right? I mean, if you're scoring average in here, you've got an 80 quiz average so far, it'll be at least that much. All right. For the exams, I'll let everything stand as it is, right? It's just whatever numbers you get. At the end of the semester, I make a value judgment on that. If you get a 90 or above in this class, you can set my house on fire and put sugar in my gas tank, you still get an A. Now, do you need a 90 to get an A? Well, put sugar in my gas tank, yes, probably, but in all probability, I'm probably going to go lower than that. However, yeah, so what it says on the syllabus, if you read it carefully, is if you get these boundary scores, you will get at least this good of a grade. You need to live your life like I'm sticking to it. Because in the past, there have been some times that I've actually stuck to like maybe the B's stay where they are or whatever. So live your life like you got to get those numbers, right? I let the test fall as they are, and I make a value judgment on that at the end. Do I make the test too hard, you know, things like this. Yes, somebody else had a question. Yeah.
What's the ratio on the testing ground for conceptual concepts versus actual math?
So what's it, run that by me again? What's the question?
Like how many questions can be like theory-based questions and then like actual?
I don't know yet. So, yeah, I would estimate, now this is actually, I can't make a promise that there will be somewhere between 40%, probably 40 to 50% would be my guess of what I call short answers. Have you looked at my old tests? Okay, so the structure will probably be, I don't promise exactly, but will probably be similar to that. So I'm gonna ask questions, basic things. I am not going to say what is theorem 8 from the book, right? That I'm not gonna do that. But if I gave it a name, or if I said, what's the theorem about blah, 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 I expect you to be able to tell me what it is. You don't have to use exact wording. What you do have to do is use clear and correct wording. One of the most important things in any math class, in fact, in any class that you all are taking, you're engineers, you're smart people. In my opinion, you're the cream of the crop. But it doesn't matter how smart you are and what you've got crammed up in here. If you can't give it to somebody else, if you can't communicate it, it doesn't do you or them any good, right? So just remember when you're communicating on the tests, right? This is a math class first and foremost, but this is not a rigorous, super hard, you know, formal math class. I expect you guys to be able to understand things and explain things to me, but you don't have to do it in a formal math way. Imagine you're making a bar bet with your buddies and you say, oh, I think this is true. You just have to convince me one human being to another as far as that goes. So I'm going to ask you some questions, like 3 pointers that are short answer, right? I might say, what's the rank nullity theorem? I might ask you to do a complicated, I think it's pretty simple, or 3 pointers, something like that. And then I will have other questions that are more like quiz questions that will be either 3 or 5 points each, probably depending on what I think about them. But I don't imagine that they will be as hard as the quiz problems. They will be a little bit more routine. So if you've done the quizzes, even if you've done badly, if you've gone back and kind of gone over it and made sure you understood what went wrong for you, I think that's going to work out well for you. I want you all to go into this with a positive attitude. Can I make this promise? I think I can make this promise. If you show up to this exam, I don't think that you can do anything that will rule out an A in this class, right? So I want you just to kind of relax your best with it. Now, you can make it a lot harder to get an A, right? But I mean, even after the first exam, I don't think A is gonna go off the table for anybody. So after this exam, and I'll communicate this to you later, I am going to give you an opportunity for an extra quiz. All you gotta do is come to my office and talk to me about exam one. You know, how'd you do? What are your goals in this course? You know, do we need to, you know, help you out or something like that? I will give you from the time that I grade the exam until the next exam, just to come by my office and just say, hey, Jim, I want the points. We sit down, have a talk, and you're done with it. I'll tell you more about this later. I tend to grade the exams fast. I don't promise that you will get these graded by Friday, though, because I have a visitor in town, but you will get them graded Monday or before, so. Okay, yes,
You said we're not given calculators or an notion or anything, right?
yeah, I'm probably gonna set up the matrices, so I expect you to kind of do it by hand. And for the most part, calculator wouldn't help you anyway, so. Other questions? Okay, yeah, and don't forget, you gotta bring your, whatever it is that you use to upload the stuff, your phone, your computer, or whatever. Don't go looking at inappropriate pages while we're in here and things like that, of course. But bring this up because it's gonna be the same as a quiz in the sense that when it's over, you're gonna have like some short grace period to upload, so make sure that you get stuff uploaded. Okay, other questions? Okay, how about the math? Surely somebody's got some questions. I'm sorry?
This is a review class?
Absolutely.
Okay. Okay.
Yeah, that's what I said.
Yeah, there's a lot to go over.
Yeah, there's a lot to go. So this, consider this sort of baby review section, right?
You just go over the main points, like the bullet points.
Well, I don't know. We'll go through the review section. So what are the main points, right? I mean, you've got to be able to row reduce a matrix, right? Everybody knows how to do that. Concepts like linear independence, things about the columns, right? So if I give you some random matrix and I ask how many linearly independent columns are, so I just give you a random matrix and say, how many linearly independent columns are there? What could you do to answer this question?
Find the.
Okay, well, let me go back to the first thing I would say. It's true for like 90%, I guess I row reduce it, right? And when you row reduce it, how many linearly independent columns will you find and how can you tell what they are? They're the pivot columns. That's exactly right. How about, what if I asked you, so so suppose I just give you some random square matrix n by n. And I asked you, is a linear transformation, so everybody understand that linear transformation, the rule for linear transformation is, what do I do for my vector? I multiply it by that matrix, right? How can I tell if that linear transformation is on?
Could we just say that the range is equal to the codomain?
Yeah, that's right, that's right. Everybody get what he said? He said, oh, Jim, it's on to if range, that is everything is covered, is equal to the codomain, right? In this case, the range would be all of So if I have a matrix like this. So let me ask you a question, so I'll take you back to your roots a little bit. What if I have a linear transformation like this? If I have a linear transformation that's taken by multiplying a vector by A, and A happens to be an M row by M column matrix, what is the domain and the codomain? What's the domain of this? Rn. How can you tell? Right. Ask yourself this. Say, self, what kind of vector can I even multiply by A? It's gotta be an n by one. That means the input's gotta be an Rn. Everybody agree with this? And what does it barf out? If I multiply this by an n by one vector, what do I get? N by one, so the codomain is. So in particular, this linear transformation over here I did goes from Rn to Rn. And so it's on to if the range is everything. Or if the columns span Rn. That's another way to think about it. Okay, be practical for me, right? You all are engineers, very practical folks. Suppose you take your n by n matrix. What can you do to it? What would you like to do? And then how do you make your conclusion that this thing is onto? Good. Row reduce it, right? And it is onto. If pivots. Yes, every row. I agree with that. That means something else about this matrix. Or it means something else about this linear transformation. You may tell me what it is. It also has to be 1-to-1. If it's onto, it has to be 1-to-1. And if it's 1-to-1, it has to be onto. But that's only because it's okay. So let me ask you this question here in the general situation. Suppose that m is less than n, then t can be, so here I'm working with words 1-to-1 and onto. T can be which one? How do I fill in the blanks here? That is correct. So if m is smaller than m, do I see that? A quick way to think about this is, in a certain sense, m is smaller than n, right? So it's easier to cover m up, right? But it can never be 1-to-1 because this is too big. Can somebody tell me why it can't be 1-to-1? You have more columns, right? You've got more columns and rows, right? So if you try to put a pivot in every column, you run out of room, right? There has to be at least one free variable. So it can't be 1-to-1. Everybody okay with that?
Yeah, and question.
Yeah.
Cause I'm I'm better at thinking about it if there's a geometric way to represent it, so. In this case, it can't have a matching, like it can't be one-to-one because there's literally more stuff in RM.
Yeah, I mean,
Is there,
that's, loose, actually, this may bother you a little bit, but actually mathematically, there's the same number of stuff in RM as RN. You know, there's input, but yeah, in a certain sense, you're kind of right. For linear transformations, there's too much for the bigger space. That's right. I think it's always good. In mathematics, they tell you, and it's true, that you can't prove anything, you can't really establish anything just by looking at one example. However, looking at one example might help. Imagine a linear transformation from all of space to a plane, right? It's easy to see that you can cover it up, right? So imagine that the plane is just the floor here and space is all of the universe. You just collapse everything on the floor. Any point in the universe sits over some point in the floor, right? And of course, here I'm extending the floor out infinitely in all directions, right? But there's no way to do that in a one-to-one fashion because there has to be more than one point in space that goes to the same point.
yeah, every point in space can get collapsed to any given orthogonal plane, which is onto. But you can't collapse it into some arbitrary plane. It has to go into that plane, which means it's not one.
Right. I mean, there are functions that are one-to-one, but
Well,
not
yeah.
linear, but not linear transformation. Linear transformation.
Okay, gotcha, thank you, that helps.
After this is probably a little anticlimactic, but. So now suppose that the number of rows is greater than the number of columns. That is correct. Imagine mapping the floor into all space, right? That can certainly be one-to-one, but it's really hard to cover everything in space just off the floor, right? And if n equals m, it's kind of it doesn't have to be. And let me point out. Let me make sure that we understand this. If n is smaller than n, then this can be on. Well, I'm sorry, this can be onto, but it can never be one point, right? It does not have to be onto. It just can be, right? For example, what if this is the zero matrix? Then it certainly wouldn't be on, right? If n equals m, if it's one-to-one, then it's onto, and if it's onto, then it's one-to-one. It doesn't have to be either, but if it's one, it's also done. Everybody okay with it? Square matrices work out well because whether something's one-to-one or onto depends on number of pivot columns and number of free variables. And by the way, what happens when you add up the number of pivot columns and the number of free variables? What do you get? The total number of columns. What theorem is that essentially? That's right. That's right. Right. Now, if you've got a square matrix, then you've got the same number of rows and columns. So that's why one forces the other. Okay. Yes, sir.
So I'm just trying to see if I understand this correctly. Is it n to m instead of m to n because you're inputting the n vector and outputting an m vector?
It's because you have to multiply. How about a numerical example? That might help. So, but and I want to define a linear transformation. Well, so let's specifically write some A. Now, this transformation should go from well, actually, where should it go from? Or
to,
what am I explaining? Because what happens, first of all, everybody okay that when you multiply, right. When you multiply our matrix, so T. Let me write down A, whatever it was, 1 minus 1, 3, 2, 1, 6. This matrix is 2 rows by 3 columns. To even be able to multiply this sucker in the first place, what needs to be true of the vector here? Yeah, it's gotta be 3 tall, right, just to make things, because the tallness of this must equal the number of columns here, right, which is why it corresponds to this. So this is like X, Y, Z. Say. Now, what happens when I apply this linear transformation to my random vector X, Y, Z? I should get a they get together and they give birth to a 2 by 1 or vector, I should say, really. And I'll have to make this longer. First row, first column is X minus Y plus 3Z. Well, I'm out of all my stuff. Now, second row, first column is 2X plus Y plus 6. And with this, I put that. And that's my linear transformation. Everybody okay with that? Okay, let's take this one apart further. This is maybe a simple thing, but it might be. Is everybody okay up to this point? Okay, fine. LU back to the section. My matrix. 1 minus 1. Okay, so let's give this a whirl. Yeah. So if I'm gonna do the LU thing, by the way, what do you know about L? One thing to remember about L is what does L stand for? Lower, right? So, and what else do we know about it?
this is perfect.
It's square, right? It's got ones on the diagonal, and everything above that is zero, right? Okay. And it's square. What size is it? It has to be 2 by 2. Because your lead has to match this. This product should get you back here. Right? What is that force on you? You're right, it is 2 by 3. Forces that upon you. It's 2 by 3. And it is the echelon form of A, right? So it's just, you don't do the reduced echelon form, you just do the echelon form without worrying about making ones be the pivot element. right? And without worrying about clearing stuff above the pivot element in the matrix. So. Anybody helping with the first column here in L? Let's build L while we kind of reduce the matrix here to help out. What's your first column, Dave? Oh, totally. First pivot column. And you got to scale it down so that this is a 1, and I'm already there, right? And by the way, look at that. I already know 3/4 of the matrix, right? I'm getting 75% on this problem. So. What do? Well, we reduce, and every time we get a pivot column, I'll get kind of a new thing. So let's reduce this matrix. So I'm going to multiply this by -2 and add. So this is going to be 1 minus 1, 3 times -2 and add is 0, 3, 0. Looks like. Actually, I didn't just know 3/4 of it, I knew the whole thing, didn't I? Because that also has to be a 1, doesn't it? It's actually, we're scaling off of this, but we divide by 3. And so, actually, that was like about the easiest LU factorization in the world. There it is, because this thing is already in echelon form, right? But I'm out of pivot column, right? That's it. And you can check very easily, and this, I totally get that probably on quizzes and on tests, you don't have time to do this, but it's good practice to get into. I asked you for an LU factorization. Does it work? You can decide that, right? Take L and U and multiply them together. If you get back where you started, I don't give a crap what the back of the book says, you're right. Right? This row, this column, I get a 1, I get a -1, 3, so ding, ding, ding. I got the first one right. And the second one should be 2, 1 for each of these. So I'm going to get 2, that works. -1 and 3, it's 1, that works. 6, 0. There we go. That's your LU factors. Yes.
But this may be dumb, because I didn't miss the lecture on LU factorization, but, can you have more than one correct LU factorization?
Yes. Yeah. Especially if you have, it's quite common if you have more, rows and columns, right? Yeah. So, I think I had one on an old test or an old quiz or something where one of the entries, it didn't matter what you put in there, right? And so you got free, because what will happen is sometimes you get rows and zeros and you'll have an entry that doesn't matter what you put.
So we're not allowed to swap rows, right?
Right, the LU factorization that we talked about, only, that actually, that's a great point. The LU factorization we talked about basically worked on doing the, doing row reduction where we're only adding multiples one row to the other. We're assuming that we could do it without row swaps, right? So if I gave you a matrix like this, there's no way you're really doing that without row swaps, right? But you can, I didn't get into this too much because you can actually incorporate row swaps into the LU stuff. But I didn't touch on that, and I'm not going to try to make you reinvent the wheel on yourself. So if I actually do LU factorization, that means I've worked it out this way and it's going to work. So. Other questions?
Can you go over finding a matrix from transformations?
Oh, well, let me see if this is what you're talking about. Like I give you a transformation and I say, it takes this vector here, it takes this vector here. What does the transformation look like? Okay, yeah. Okay, let me start with the easiest case. The easiest case is where you have a send basis. So suppose I have T, And let's suppose the team of E1 is vector. And actually, later in this course, we're gonna do more complicated. We're gonna learn how to do this even more efficiently. Y'all remember what I mean by E1, E2, and E3, right? This is 1, 0, 0, 0, 1, 0, 0, 0, 1, right? Standard basis. Let me just make up some crazy crap. 2, 2, 7, minus 1, 4, 8, 5, 0, negative 6. So, question. Find the standard matrix. If I did this one's an easier one. Yes.
So you just slap them all together next to each other.
Yeah. We're gonna do some slapping. 2, 2, 7. Minus 1, 4, 8. And 5, 0, minus 6. Again, this is easy to check. Just put in 1, 0, 0 here, and it goes to 2, 2, 7. Put in 0, 1, 0, it goes to the second column, and 0, 0, 1 goes to the third. Everybody okay with that? Well, let me give you one that's got a little bit more meat. Let's do this one. Um, yeah, so, well, let's see, I'm do a good basis here. Yeah, yeah, so these three actually are bases. So, let me make it. So this is 1 minus 1, 3. One. And let's go. So I want to find out what the matrix of this is, right? This linear. Okay, so how do we go about this? I mean, now I haven't started with the standard basis, so you just can't throw in columns, right? You got to figure out what's going on. How do we do this?
On the quiz, I did the ABC.
Right. Let's use a little linear algebra, right? This is after all a linear algebra class, so we might as well use some of this. What do we need to do? Well, we need to figure out how how to figure out what the matrix is. So what do we know? You said the ABC thing, so let's see what that means. C U D W X. We're gonna get a lot of equations out of this. This is what the matrix is. And I've got 9 things to figure out, right? Well, let's look first at this. When you multiply the spectrum times 103, you should get this, right? So A, B, C, U, D, W, X, Y, Z. I think that we're gonna see some patterns here pretty quickly. 103, that should give 1 minus 1, correct? So this gives me some equations here. What does it give me? It gives A plus 3C is equal to 1. It gives me U plus 3W is equal to -1. And it gives me X plus 3Z equals to, right? So I've got 3 equations, but I've got an obnoxious 6 number of variables up there, right? And there's some things that I kind of missed out. Okay, need more information. Okay, what's the second vector? 0, 1, 1. And that should turn out to be 2, 2, 1. So this gives me some equations here. I guess it gives me B plus C is 2. It gives me B plus W is equal to 2. And it gives me Y plus Z equal to 2. Thank you. 1. There we go. But cool. Okay, finally, A, B, C, C, U, V, W, X, Y, Z. Times the last vector, which is 2 minus 1, 1, is equal to 0, 4 minus 3. And this gives me 2A minus B plus C is equal to 0. 2A minus B plus C is 0. 2U minus B plus W is equal to 4. And 2X minus Y plus C is equal to -. Everybody okay with that? Gravy on popsicles. Nobody wants to do this, right? I mean, look at all these equations. What should I do? Is it time to punt?
Matrix.
Yeah.
Okay, so I went a little ahead and grabbed the top, for the A, B, and C equations, at the top of each of them, and put them in a matrix, and if you do that, you get like a matrix that is the transpose of like the answers, or the input vectors.
Okay, so let me,
That probably doesn't make it, yeah.
of course, these 2 equations don't help you anything with the A's and C's, right? So let's get all the stuff that has A, B, and C bundled together, right? And notice we have a U and V kind of bundled together. What can you say about these equations? They're all the same. The only difference is notice this is A plus three C is something. This is U plus three W is something, and this is X plus three Z is something. This is all the same equation. Everybody agree with that? So, can anybody describe what we might want to do here? Well, for the first one, we're solving A plus three C is 1. B plus C is equal to 2, and 2A minus B plus C is equal to 0, right? And then we do the same thing where we replace the 1 by -1 and the 2's left alone, and then 0 by 4, and so, right? Why don't we see if we can do this all systematically at once? Because it's the same equation, it's just different outcomes, right? So let's try this. Let's put these in an augmented matrix. Let's see, what would I have? 1, 0, 3. And I'm going to have 0, 1, 1. And then 2 minus 1. Everybody agree with that? And the only differences is what's on the right side of the equal, right? Everybody okay with that? So let's do this more generally. Let's call this, let's call this K. We'll see if we can just kind of do it all at once, right? Instead of just doing one, we'll solve several. All right, so if I'm going to do this, what's the first thing I should do? Right, I use that 1 to kill that. Sure. Everybody agree with that? -2 and add. So this matrix becomes 1, 0, 3, 0, 1, 1, M, and 0, minus 1, 1, and minus 2. Oh, yeah, this is something else. This times -2 and add. So that's going to be what, -5? And what goes over here? N minus 2K. Everybody else? Okay, so now what? What's the next moving thing? Yeah, it looks like I can just take this out. Right? I agree just by adding this to the bottom, I can get this equation here. And this new matrix here. 1, 0, 3. Okay. 0, 1, 1. M. And when I straight up add here, I get 0, 0, minus 4, and I guess N minus 2K plus M. That look right to y'all? Okay, So. I think at this point, I'll probably want to back some. Right? Because what does it say? It says, -4, let's call it, I know I have different variables for this. Say -4x3 is n minus 2k plus m. So tell me what x3 is. This equation is x2 plus x4 is equal to, I'm sorry, x2 plus x3 is equal to m. And so x2 is m minus x3, which is m plus n minus 2k plus m. Good. And finally, if I can fit it in here somewhere, do one of these equations there. X1 plus 3x3 is equal to k. And so x1 equal k minus 3x3. And x3 is this. So x1 is equal to k, and then minus 3 times this is 3/4 n minus 2k. Now, how do we go back and figure out what our A, B's, and C's are? Well, remember, this is solution. So for the A, B, and C, right? A is the role of x1, B is the role of x2, C is the role of x3, and K is 1. M is, what's M and N? 2 and 0. Everybody agree with that? And so this formula should give what we want. So for example, I don't think we're going to finish this one up, but you probably try to finish this up. If K is 1 and M is 2 and N is 0, then X3 should be, or that is C should be in this case 0 minus 2 plus 2, which is 0, so C should be 0. B, which is x2, should be this thing. So this should be, well, I guess we're going to get a 0 here again, aren't we? Because that's going to be 0 minus 2 plus 2. So that's going to be a 0, and M is 2, so B is 2. And A is equal to whatever's left over. This should be 0 plus K, which is 1. And there you go. Use this on the other ones and see if you can get the matrix and check that it factors properly. And let me know if you don't. Yes, sir.
So it's not really your point that that's the training code that we started. The output, is there a relationship between that? Like
There is, but it's a little bit subtle. So bring that up again and I'll talk more about the relationship with transfer. we're gonna talk about that later, but not yet. Yes. I like the test, and I'm working out. And I also will let you break this. Like, so that might tell you something. You know, I'm not saying that I'll never screw up, but if I do, and I do something equal like that too, and you're not going anywhere, my suggestion is move on to the next problem. It's possible I made a mistake, right? And then I try to check the time. And if I do screw up, that makes me extremely upset. That's great.
But